Let's move to the third section, flow process. In this section, we are going to talk about when there is only one driving force applied or acting on your material system, how to quantitatively describe this flow process by using the driving force, flux, and corresponding uh, entropy production. And in the third section, we are going to talk about if the driving force, there are more driving force, for example, like two or more driving force, how to deal with or how to quantitatively describe this flow process. Are there any like interference or coupling effect between two driving forces and corresponding or induced flux? So let's talk about the third section, just only one driving forces or one driving force. So how to quantitatively describe the flow process? First thing come out from your mind probably will be you have flow, something flow into your material or flow through your materials, right? So probably first thing come out from your mind will be there's definitely a driving force acting or apply uh, on your material system. So they could be chemical potential gradient to drive the mass transport, or temperature gradient to drive the heat flow, or electrical potential gradient to lead the electrical flow passing through your materials. Besides driving force, a driving force, they'll definitely drive something. So drive the specific flux can be the heat, can be the mass, atomic flow, or the charge, which means the current passing through your materials. So the unit for to describe the flux would be the numbers or the physical entity passing through a unit area in the unit time period. Even though you have a driving force induce the flux, but depending on different materials properties or transport mobility or inertia of a systems, we believe the flux will be different. So transport mobility or resistance can be considered as a diffusivity to describe the mass transport, thermal conductivity to describe how fast or how slow the heat flow is, or conductivity to describe the electrical property of your interesting materials. So it's conductivity. So now we know that if you want to describe a flow process, you need to have driving force, flux, and material properties, such as like the transport mobility or resistance. Are there any equations to correlate all of them? So prop and which energy function is best for it? So is that possible to have a universal equation to correlate them and also quantitatively to describe the energy state function change to allow us to well describe the kinetics process? So the energy state function, the answer is none of them. But some people probably will ask why. Do you remember what's the energy state function include would be? Like for example, like can be like UHAG, right? Internal energy, enthalpy, Helmholtz free energy, or Gibbs free energy. If we deal with under the constant pressure and temperature, the energy we're going to choose probably will be the Gibbs free energy, the change rate in the Gibbs free energy. So I just use this as an example to describe why energy state function is not the best choice to describe the flow process. So the energy state function, do you remember that we have a dg, the change in Gibbs free energy equals to negative entropy times dt plus V volume times dP, the change in pressure, plus the extra term, summation term regarding to U times the chemical potential times the change in composition. You need to sum them together, then you can get the total changes in Gibbs free energy. But if we want to describe the kinetic process or flow process, the most important part would be the change rate, which means the time dependent. So what's the change rate? So we divide it with dt together. So we are going to have a Gibbs free energy change rate or change rate in Gibbs free energy. So let's check whether we can use this change rate, Gibbs free energy change rate, to describe a flow process. Is that easy to do that? Based on this equation, you got the negative term plus positive term of plus volume times the pressure change rate plus an extra term, which is correlated with chemical potential change rate. But it's quite difficult, right? Because in order to get the exactly value for the Gibbs free energy change rate, you need to know this one and times the entropy, and also need to know the pressure change rate times the volume. And volume is not easy to measure as well. And also you need to know the composition change rate times its corresponding chemical potential for specific atoms. So you have a negative term plus the second term and plus the third term. So as long as you know the exactly value for each term, then you need to sum them together. Then I will then you have chance to know the change rate in Gibbs free energy. So it's quite complicated. So in your textbook, they say probably that'll be better if I can choose the change rate, which is um, always like a positive, something like that. That will probably more easier. So they suggest how about use the entropy, because based on the second law in thermodynamics, entropy always larger, or entropy change you always larger or equals to zero. So in your textbook, they suggest that how about is that possible to use entropy is a to describe the flow process. The entropy means the entropy, the change rate in entropy, or the rate of entropy change or entropy production. Is this uh, pro, uh, is that possible to use like the rate of entropy production to describe the flow process? And finally, you know that the answer is yes. So, and like got this beautiful equation. What does yes? I will prove this by using three like different kinetics process or flow process. But before that, I'm going to tell you that they got this beautiful equation is we have a temperature, we use a temperature times the rate of entropy production per volume equals to the dot product of the flux vector and the force vector，这个是内积，然后这是乘，也就是温度乘上我的熵的每单位体积产生速率，每秒或是每单位体积产生多少 entropy 会等于我的 flux 跟它的力的内积，那这是内积，那这单纯是乘。Okay, so like they finally like they have this beautiful equation to link the driving force the flux, and also transport mobility actually is embedded into the flux, and sigma dot rate of entropy production together to describe how fast or how slow this kinetics process is. By using like this equation, you can simply calculate the sigma dot, which is a rate of entropy production, to describe how fast or how slow the system generate the entropy. If you have larger sigma dot, which means that the system generate entropy fast than the other one with a smaller one, right? So this is how, so the purpose here is get the sigma dot to calculate the sigma dot by using this equation. But before we really calculate the sigma dot, first of all, probably I need to persuade you this equation really works for different kinetics flow process. So I'm going to use like 3 different kinetics flow process to demonstrate that this equation really works. So the first one would be the heat flow process. The second one would be the electrical flow process. And the third one would be the mass flow process. So what is the heat flow process? What we have here is we consider 2 heat chambers at temperature T1 and T2, and we assume T1 is higher than T2. And we're using the metal bar to connect these 2 chambers. And as you image that, or you think that after a while, the heat, I believe, not after a while, the heat, as long as I put this metal bar to connect these 2 chambers, the heat will flow from left-handed side toward right-handed side. We will get the heat flow. But after a while, when the system reach steady state, which means that we have the steady heat flow process, flow from hot side toward to cold side and reach steady state, which means that we have steady heat flow process. Under this situation, we need to prove that this equation works. Then we can calculate the sigma dot, which means that what is the rate of entropy production in this kind of heat flow process. So this is the first case. And the second case, as I mentioned before, is electrical flow process, right? So how to have the steady electrical flow process. So the setting will be like this. We also have a metal bar with length L and area cross section area A, and I connect this material to the battery. So that will lead, we have the electrical potential gradient V1. We assume V1 larger than V2. So that will lead the current passing through left-handed side toward to right-handed side. And after a while, when the system reach steady charge or current flow, then we have steady electrical flow process. So based on these settings, I also need to prove that this equation works and help you to how to calculate the sigma dot, which is the rate of entropy production. So this is the second example. And the third one, also the last one, will be the mass flow process. So how to have this one? So we also have a material, a bar, a metal bar or something. We have our materials here, and with the length L and area cross-section area A. And this is mass flow process. So I have different composition of AA turns XA1. Concentration is larger than XA2. So then that would lead the atomic flow process from toward to right-handed side. Due to this higher composition of atom A have a higher chemical potential than lower concentration of A at A2. So that will lead the atoms moves from higher chemical potential side toward to lower chemical potential side. This will have a atomic flow. As time increase, then when it reaches steady atomic flow, this system's steady mass flow process. I also need to demonstrate that under these situations, we can use these equations. Equations can well describe this process and also help you to get the sigma dot, the rate of entropy production. So by using these three different kinetics flow process, first of all I need to demonstrate that these equations works and also help you to get a sigma dot. And by comparing the sigma dot in each case, then you can have some idea which kinetics process is faster, which is slower. Okay, so let's move back to the first case, is the heat flow process. As I mentioned before, we have a metal bar and have a hot reservoir on your left-handed side and a cold one in your right-handed side. Because T1 higher than T2, so that will lead the heat flow passing through this material and toward to right-handed side. So we got a quantity of heat dq flow from T1 to T2. And this is what we are going to prove, right? And it have entropy here and also the heat flux, J capital Q. And also, as I mentioned, driving force for heat flow is a temperature gradient. So in order to show this equations works, and this is entropy, so I need to have some equation to demonstrate that we have entropy term inside this equation. So what are there any equation or laws you learn regarding to the entropy production and also some T1 and T2? So probably you will think about what? Second law, the change in entropy equals to the negative. Oh, okay. The change in entropy equals to the change in heat divided by temperature. And the positive term and the negative term means lose the heat or get the heat. So for the hot chamber, it lose the dq. So we got the change in entropy, Sy equals to the negative lose the heat, dq divided by T1. And for the um, cold reservoir, we got the ds2 will be equals to they got some heat dq, right? So plus dq divided by the temperature, so it's T2. So we can sum them together to get the total entropy change in this for the systems. So the net change in entropy, we just simply sum them together. So what we have is we sum this plus use this plus this one. So we got this equation, and we just want to simplify them into here. So we got the T1 minus T2 divided by T2 T1. But here we know dq is positive. T1 larger than T2, this is positive as well. And T1 times T2 is positive as well. So the net change in entropy is positive. Okay, so this is what we have here. We have a relationship between the entropy, net entropy change. T1, T2 probably can be something related to a driving force or something. And we also have a dq is the heat flow. So this is not our final goal because in this case we just prove this heat flow process produce the entropy that lead to entropy increasing. But also we got that the heat flow, this phenomena will lead or produce the entropy. But I want to show you this equation works, right? So probably from here to here, we do need to do some like mathematic calculations or multiplications. So I just make some assumption here, the length of a metal L, cross-section area A, but I just want to sigma dot actually by the definition is entropy change per unit per unit time and per volume. So volume will be the volume of a metal, so it's A times L. So and net entropy change you already got it here, right? So it's this value. So you just put let's dq T1 minus T2 T1 T2. This is a ds, and I also put the term just copy delta T and L here, right? So I already have a sigma dot equals to here. And if I want to prove this equations work, so as long then I need to have move T to here. So I need to like find the JQ FQ divided by T, something like that. So as long as I can show this equation equals to JQ times FQ divided by T, then this equation works, right? So let me do some like combination for some specific terms. So what we have here is JQ is the heat flux, right? The heat flux is per area per unit time. So I put this together. Then this is equals to JQ. So we have this term already. And what we have here is this term, right? So T is at the bottom. So what I have here is I have T1, T2. So I put the T1, T2 here. And the remaining term is a T1 minus T2 divided by L actually is a definition for temperature gradient. Gradient is divided by the length, right? So this is a temperature gradient. Okay, so I have a flux, heat flux, and the remaining here is a negative temperature gradient. Negative temperature gradient. Why is negative? Because we use a T1 minus T2. And what's a T1? T1 is here, and the heat flow is go this way. And we usually will use the ended temperature to minus the beginning or starting point, right? Should be T2 minus T1. But here, here we got a T1 minus T2, so we have a negative gradient term. The gradient usually will be T2 minus T1, so we have negative, so that will be go this way. And the bottom term, what we have here is we have T1 and T2. But we hope that we have like just one T, right? So we just do some, this is just the mathematic trick. We use T1, T2 and assume a new parameter we call a Tm. We use a square root of T1, T2 equals to Tm. So here I can have a Tm square. And I put a 1 Tm here and 1 Tm here. So compared to these equations, what I have here is temperature times sigma dot equals to flux. And the remaining or left term is we call a driving force for heat flow. So the driving force for heat flow, not just the temperature gradient, also divided by the temperature, which is Tm. Okay, so we prove that in under this like deviations, we demonstrate that this equation is work. This equation works for mass transport. Oh, not sorry, for heat transport. So we got the temperature times the sigma dot equals to heat flux dot or times the driving force for heat flow. And the driving force is not the general you think is a temperature gradient. No, it's the negative temperature gradient divided by temperature. So this is serving as a driving force. So first case, we successfully to prove that for steady heat flow process, this process can use this this equation can well describe this steady heat flow process. And in the meantime, you also can use this equation to get the sigma dot, the rate of entropy production per volume. Okay, so let's move to the second example, which is the steady electrical flow process. So as I mentioned before, due to I just connect the our metal bar or our materials to the battery and have the steady current flow passing through these materials. As long as which demonstrate that we have reached the steady flow process. So I also need to demonstrate that this equation works. So no doubt that I need to have sigma dot as well, and the flux here will be the current, and driving force usually will be the chemical potential, electrical potential gradient. So let's do something. In order to have the sigma dot rate of entropy production, I need to know that as long as I flow or current passing through the metal, it usually will generate some heat. So we call it gel heating. As long as I have the heating, I mean, I have the heat here, generation some heat that can lead or link to the entropy production by according to the second law in thermodynamics. So I am going to use this like a gel heating rule or Ohm's law to try to have a sigma dot. So according to the Ohm's law, the power generation rate per unit volume is due to the unit for sigma dot is also the per unit volume. So the power generation rate per unit volume can be rewritten as like this: power generation rate, so a rate per unit volume. So I generate some heat here, right? Delta Q is because you be due to the Ohm's law. So based on here, I know the rate, generation heat rate, heat generation rate equals to I square R. It's like a P equals to I square R. So I have I square R here. And just divide, I mean, just separate I square R into, because what I need to do is I need to have a current density and a driving force. Current density, so I only need one I current density. So I put the A here, L here, and I just will need one current here, then I can have a current density. And IR can be rewritten as delta V, so it will be V1 minus V2. So here I have a current density, then the second would be electrical potential divided by length gradient. And also V1 minus V2, but currents go this way. So usually gradient will be V2 minus V1, V2 minus V1. So I need to have negative term here. So what we have here is a negative electrical potential gradient. So here I successfully have a current density times, or you can say inner product of current vector times the force vector. And the force vector here is negative electrical potential gradient. So now I already have this, right? So if I can rewritten this term to equals to this one, then I can say, I can prove this equation works, right? So can I, by using this one, can I link with the entropy? Yes, right? Because this is heat, the change in the heat. So based on the second law in thermodynamics, you got like the dq can be rewritten as T delta S. So I can use the T delta S to represent it. So I got the T delta S and the AL put to the upper. Then delta T at the bottom. Why? I need to have a temperature times the entropy production rate per volume. Entropy production rate per volume. so it's perfect. So we successfully to prove that um, temperature times the sigma dot equals to the inner product current density times the current density and the negative electrical potential gradient. So based on this, we confirm that this equation also can be used to quantitatively describe the steady electrical flow process. And based on these results, we can get the sigma dot as to quantitatively describe this kinetics process. And also this case tell us that electrical flow always produce or generate entropy, and how much entropy be generated. So we can, as long as you know the temperature, JQ and FQ, then you can get the sigma dot. Okay, so this is for the electrical flow process. And the last one would be the mass flow process, which we have the metal bar with different composition. And on your left-handed side, we have a higher composition of A10A compared to right-handed side. So here, the driving force will be the chemical potential gradient and induce atomic flux. And in this case, I also need to prove this equation works, can well describe this steady mass flow process. But as I remember, as you remember that the driving force is chemical potential gradient. So that's must the relationship between the composition of A10A and is chemical potential difference, right? Do you remember any equation you learned before involve like the chemical potential versus a composition? For example, like composition change lead the chemical potential changes. Do you have this idea? So I'm going to give you a quick review for kinetic, also for thermodynamics, as the relationship between the chemical potential mu and the composition x. So I'm going to show you how to derive this how the chemical potential changes with composition XA. This is our final goal, final results. But it's a quick review. I'm going to show you how to do that, how to derive this equation. So consider we have AB alloy with the composition XA at constant temperature and pressure, constant T and P. So the energy I'm going to use will be the Gibbs free energy. So the Gibbs free energy of this alloy can be written as Na times mu A, chemical potential of A10A times how many A atoms I have in the system, and plus MB, mu B is a chemical potential of atom B times the numbers of atom B I have. And also some kind of, based on the thermodynamics, you also can rewritten as mu A, Na times mu A0 plus MB times mu B0 and the mixed entropy minus T delta S mixed entropy. So it's what is the mu A0, which means that the chemical potential of A10A in pure A metals times how many atoms I have. The same idea for mu B0 is a chemical potential of atom B in pure B metals. Okay, then because this is alloy, so I like a mix A and B together. AB atoms together, so I have minus because I'm mixing will lower, will lower like the total free energy, so we have a minus T delta S mix. And delta X mix, which means the entropy change during mixing this process. Based on the thermodynamics, you can rewritten as a Boltzmann constant times log omega. Omega is a combination numbers, so we have a n number Na plus Nb factorial of Na plus Nb divided by Na factorial Na and factorial Nb. So this is the combination total combination number by mixing A and B together. So you based on this, we also know this log n factorial and equal, as long as n is very large, we can rewritten as this way. So based on this idea, this equation, this results can be rewritten as this. So this one is quite familiar with you, right? It's a negative k na log xa plus nb log xb. So this is the entropy change during mixed process. So we just put take this inside here, substitute delta as mix with this, and we can rewrite this equation. So we got the total gives free energy for this AB alloy. It can be rewritten as this one. We got the pure A, pure B, and mixing term. So what's the chemical potential of A10A at specific composition XA? Is we just partial gives free energy, partial with Na. What's the meaning for chemical potential of A10A at XA? Which means that when you added one more or unit moles of A10A, how much like what's the what's the change in Gibbs free total Gibbs free energy we call mu A at XA. And so if you directly use this term to partial with Na, so the only thing you have here would be this term. So you partial with Na, so you got mu A0 here. And this one is nothing really related to Na, so 0. And this term will be K, if you partial with Na, so you have a KT log XA. And this term also nothing related with Na. So that's why we have this final equation demonstrate that how the chemical potential of A10A changes with XA, which is a composition. So as long as the concentration or composition of A increase, the chemical potential of A10A increase as well. Which means that if you have more higher concentration of component A, the chemical potential of that the A10A is higher okay? So the other deviation is some people probably will use this term to partial with Na instead of this one. So you will got you can have you will have the other relationship link with the partial entropy. So we call a partial atomic entropy is you directly use this term to partial with Na. So you also have the mu A0. We don't have this term and partial with Na. So this term can also be rewritten as mu A0 negative T delta as mix partial with Na. So you got the SA bar. This is a partial atomic entropy A, which means that when you added one more or unimoles of A10A in the system, what's the um, entropy change during this mix process? We call a partial atomic entropy. So based on these results, we know that if you, but this is we have negative term, right? So if you have a higher composition of A10A, that will lead the partial atomic entropy decrease, but chemical potential increase of A10A。OK，所以在这里的话，我想特别讲就是，大家对于化学位能 A 原子的化学位能的解释，常常我会问说什么是 mu A，就是 A 原子的化学位能。其实它在定义上就是那个，当你加入这个，把这个一摩尔一个单位的 A 原子加入这个系统的时候，整体系统的 Gibbs energy 的变化量，就是这个A 原子的化学位能在这个成分下面的。 那我们刚刚其实就只是秀了这个推导，那最主要是想秀给大家看说，当 A 的成分增加的时候，它 A 原子在里面的化学位能事实上是高的。所以它也就不稳定，所以它会倾向去低浓度的地方。这是说明了为什么，会有扩散这件事。就是在大部分的 case 里面，大家看到的都是化学位能高的原子，浓度比较高，就是因为，就是 Xa 比较高的时候，其实它的 chemical potential 事实上是比较高的。那这张 slide 又同时把就是 entropy partial atomic entropy 就是放进来。所以可以知道说什么叫 partial atomic entropy。就这个定义的话，其实也是加入1单位的 A 原子的时候，我的 mix 这个 entropy 的变化量就是 SA bar。所以可以从这里知道，就是当如我刚刚说，就是当 A 原子浓度增加的时候，化学位能是那个原子的化学位能是高的，那 entropy 是低的。就 partial atomic entropy 是低的，那就只给大家做参考。那我们主要要知道是这个关联性，因为等一下 driving force 事实上就是 chemical potential 在 drive 嘛。所以我们来看一下。So let's move to here. You already have some concept from previous slide. So who drive this chemical potential? I mean, who drive this like a mass flow process is chemical potential gradient. So what's the chemical potential difference between A1 and A2? So I will say the atomic flow is go to right-handed side. So I will say the delta mu will be XA2 minus XA1. Right? Chemical potential at XA2 at A2 minus chemical potential of A10A at XA1. So as we mentioned before, just copy the results, copy the results from previous slide. So I just use like copy mu A0 plus KT ln XA2 is this one. And this is mu A0 plus KT ln XA2. So mu A0 delete. So what I have is KT ln XA2 minus KT ln XA1. So it's this results. Right? Regarding to the second term, regarding to the partial atomic entropy, so I just copy this one. Mu A0 minus T SA2 is here, right? And also minus the mu A XA1 can be rewritten as mu A0 minus T SA1 bar. So mu A0 delete. So I have this minus this one. So I got a minus T, this minus this one. So we have a delta SA. Okay. And as you know, delta SM is a lot much positive. So I already have this chemical potential difference will link with entropy production. But this is for unit numbers of atom for unit numbers of atom A. So in order to also want to show you this correct, so I just write down absolute temperature times the sigma dot equals to, so I copy the T delta SA bar is the unit number, right? So I have no idea how many numbers of atom A I have, so I need to delta NA. So here I have the T times sigma dot is the total numbers of entropy change rate per volume. So I got this is T times sigma dot per volume. Then I rewritten it because my purpose here, my target is converted them into flux and driving force. So T times SA bar here is equals to chemical potential difference, negative chemical potential difference. Copy this one, copy. I just copy this AL, T and numbers. And my target is here. This is atomic flux. As we mentioned before, the unit for atomic flux is the numbers of atom per unit area per unit time. So I just put here, and here together, and L and chemical potential to outside here. So I got this is atomic flux, and the rest of part for sure is we call a driving force is a negative chemical potential gradient. So I successfully to demonstrate that in the steady mass flow process, also absolute temperature times the sigma dot, which is the rate of entropy production, equals to the atomic flux times the driving force. And the driving force here is a negative chemical potential gradient. So atomic flow lead the or produce the entropy. Okay. So because this equation can well describe this phenomena. So as long as I know this, and this, I can calculate the sigma dot. So give you a quick summary here. The rate of entropy change or the rate of entropy production, instead of not the free energy change, can be used to well characterize this irreversible kinetics flow process. And not only the heat flow, electrical flow and mass flow can lead to the production of entropy in the system. So I'm just give you I just summary all the information or equation we have here is absolute temperature times the entropy production rate per volume equals to the flux times the is driving force. So I just summary here. So for the heat, the driving force is the negative temperature gradient divided by T. And for charge, it's a current density times the negative electrical potential gradient. For atomic flux, it's atomic flux times the negative chemical potential gradient. Okay. So this is, and I also just want to use some symbol F capital Q, F small q, and Fi to represent the different driving force. Okay.